two misconceptions about Newton's third law. Now, we have met misconception here before, and perhaps you were under the impression that misconception is a person who has misconceptions about physics. But that is a misconception. Misconception actually understands physics very well and devotes a portion of her time to promoting science education and helping to clear up common physics misconceptions. And today, she's here to help you identify and avoid two common misconceptions about Newton's third law. Misconception number one. People often think that when they hear this idea of forces being equal and opposite, doesn't that mean somehow they'll cancel each other out, so nothing moves at all? And the way to clear that up is to recognize that the forces of a Newton's third law pair always act on two different objects. For instance, suppose you've got Newton here kicking a soccer ball, and the wrong way to imagine this is to imagine those two forces both acting on the ball. Like, here's the force of Newton's kick on the ball and the force of the ball back on Newton. If you picture both of those forces acting on the ball, it does look like they'll cancel each other out and the ball won't move. But that's wrong. The two forces act on the two different objects, the ball and the foot. There's your Newton's third law pair. So just as the foot pushes the ball, when you kick a ball, you feel the ball push backwards on your toes. You feel that pressure on your toes. That's the other force on you in the Newton's third law pair. Example number two, rocket propulsion. What enables a rocket to move itself in space is by ejecting exhaust. And the exhaust has mass, so we can treat that exhaust as a separate object moving off to the left as the rocket is propelled to the right. So we have here a Newton's third law pair. The force on the rocket due to the exhaust and the force on the exhaust due to the rocket. Misconception number two. When encountering scenarios, it's easy to imagine that the bigger or faster thing in a collision will always exert more force than the smaller or slower thing. And that's not the case. The size and speed of the objects do not change the conclusions of Newton's third law. So for instance, if we have, say, a collision on the highway between a truck and a little bug zipping along. So suppose the truck is moving at 70 miles per hour. Here comes the windshield about to collide with our little bug here. During the impact, the force on the bug due to the truck will be equal and opposite to the force on the truck due to the bug. Now, the bug is going to come out worse for the wear here. The bug's going to get splattered, but the windshield will be fine. So it's easy to think that the windshield must be exerting a bigger force on the bug than the bug is on it. But the situation is a bit like the headbutt here, where the windshield is like the frontal bone of the skull and the bug is like the nasal bone here. They're both going to feel equal and opposite forces in that collision, but the bug's going to get smashed. The collision might involve, say, 10 newtons of force. 10 newtons of force won't do anything to the windshield, but 10 newtons of force will squash that bug. Another way to understand this is to recall Newton's second law and bring that into play. If we apply that to the bug, the acceleration that the bug feels during that impact will be due to the force on the bug due to the truck, but divide that by the tiny mass of the bug and you'll get a huge acceleration for the bug as it sort of gets carried along with the truck. However, apply that to the truck, and if the truck feels the same exact force but has a huge mass, it's going to have just the tiniest backwards, leftwards acceleration when it hits the bug. You won't even notice that tiny acceleration that the truck has. So in the collision, there is a very different effect on the two objects. They do have very different accelerations, but they're experiencing exactly the same force, according to Newton's third law. Last example. The Earth's gravitational pull on the moon and the moon's gravitational pull on the Earth. Earth is much bigger than the moon. So people often imagine the Earth must be pulling harder on the moon than the moon is pulling on Earth, because the Earth's bigger. But let's investigate. Suppose at first that the moon has a mass that's equal to the mass of the Earth. These would be our little masses here. So if their masses are equal, then they would be exerting equal and opposite forces on each other. But suppose then we add more mass to the Earth. Add a mass to the Earth. Now this mass and the moon's mass will be interacting with each other, exerting equal and opposite forces on each other. Add some more mass to the Earth. Now this mass and the moon's mass will be exerting equal and opposite forces on each other. So there's another third law pair, and you get the point. You see that when we add up the forces, these three forces on the Earth due to the moon add up to this net force on the Earth, and then these three forces on the moon due to the Earth will add up to an exactly equal and opposite net force on the moon. So they do exert equal forces on each other, even though the Earth is so very much bigger. This picture, I think, explains that. Oh yeah, and in case you were wondering, Newton was, of course, famously a rabid fan of Manchester United.